So, as you know, we've spent the last few days reviewing the basics of systems and systems of equations. Now, we're going to pause on that for a few days and begin what seems to be a whole separate conversation on matrices. Well, what you're going to find out at the end of this conversation is that there is a direct connection between systems and matrices. But we got to go through some of these essential ideas. We have to learn some things, and then I promise we'll go and we'll figure out why do we need a matrix? What does it have to do with a system? I think you'll like the answer. So matrices. What is a matrix? Well, if you've not had too much exposure to them, let me introduce to you that basically a matrix is an array of numbers. An array of numbers is really just an organized group of numbers. I can have numbers that aren't in an array, maybe like a bag of numbers, like a bingo bag. That's not an array, it's not organized. You see, a matrix, when it's organized, it's going to be organized in rows and columns. And here's a real simple matrix. I encourage you to write it down. Basically, we put 12 elements in that matrix. And as you can see, it's organized. How many rows and columns does it have? Well, that's going to be what we call the size of the matrix. Also, the word size can be, we can use the word order. So the size or order of a matrix is always defined as the number of rows, then columns. Now, just to make sure everybody knows what a row is, pretty basic stuff here, but we've got a matrix that contains 3 rows. And just so everybody knows what a column is, we have 4 columns. So we would say that this matrix is a 3 by 4. Pretty easy so far, right? What if we wanted to maybe do something with some matrices? Perhaps maybe I wanted to find x and y if I had 2 matrices that were equal. If matrices are equal, we would discover that we would not discover, but we would realize that they have equivalent corresponding entries. That's just kind of a fancy way to say that every number in the first matrix obviously is going to have to be equivalent to the corresponding numbers in the other matrix. So let's create a little problem here again where we're going to find x and y, but we need some matrices. So here's a matrix that contains y minus 3, 2, and 1, then 4, y, and 0. So we've got a nice little matrix that has 6 entries, and we're going to say that it is equivalent to a matrix that contains the entries x, 2, 1, and 4, 2x, and 0. And so these two matrices are equal. Their corresponding entries are equal. Can we try to find x and y? I have a feeling that we certainly can. Let's just use some basic principles here that if I have my first entry here, actually we would say that it's the entry in the first row, first column, then it definitely would have to equal the corresponding entry that's in the first row, first column. And so we get a little simple statement that says y minus 3 equals x. Do you see something else we could do? Some other entries that are corresponding? Remember, we're trying to find x and y. So yeah, it would make perfect sense to say that the numbers that are in the second row, second column, have to be equivalent. And so we end up with a simple statement that y has to equal 2x. Now notice that all the other numbers are obviously equal, so I don't need to do anything with them. But what I do need to do is realize that what we've just created here is a little system. A little system of equations. I have a feeling that you could solve this. Do you want to go ahead and try to solve it? You should be using a really basic substitution method, right? All you're going to do is just substitute your 2x in here for y. And go ahead, you do it. You don't need to watch me, although I'll follow along behind you. And so as we work our way to finding x, we should discover that 3x is going to equal 3. And of course, you can take x equaling 1, and you can very easily substitute that back in to your second equation. So we get y equals 2. Now, I have a feeling that what we did there isn't too earth-shattering for you, but it gives you the idea that matrices have entries, and if matrices are equal, then their corresponding entries, of course, have to be equivalent. Let's continue to look at some matrix essentials by finding x and y through this little matrix problem. Now, I'd like to show it to you first, so just jot it down with me. Notice I have a 2 that's in front of a matrix that contains 6, -3, x, and 0. Then a subtraction sign with a y, that's the letter y, that's in front of a matrix that contains 2, then x, 5, and 4. And we'll say that that equals a matrix that contains y, -2, -22, and -16. Try to squeeze that -16 in there. Now, this problem, as you can see, we've got a little bit more going on. I'd like to talk to you about these numbers and a variable that's in front of both of these matrices. You see, those numbers and variable, they will be part of what's called a scalar multiplication. Now, scalar multiplication, really just a fancy word for do the distributive property, but we use the word scalar for a particular reason because that's going to be different than another type of multiplication that we'll do in just a moment. So in any case, pretty basic. Here again, kind of common sense. Just take your 2 and multiply it to every entry. So we're just going to end up with double each of these. We'll go ahead and multiply by 2. And we're also going to multiply by y. You might see here that I'm choosing not to think of it as a negative y. I don't really want to have a negative sign that comes inside the matrix and sort of overloads the matrix. So we'll just distribute a regular y, and we end up with, of course, some new terms. Still, this entire thing is going to equal y -2, -22, and remember, -16. Scalar multiplication. Now, what about the other operation that's contained here? We see an addition-subtraction sign that is between the two matrices. Well, matrix addition and subtraction, probably what you would suspect, just basically adding and subtracting your corresponding entries. Now, if we're trying to find x and y, then it would probably be smart to add and subtract entries that contain y. So here we go again with the first entry that's in the first row, first column. And because of subtraction, we're simply going to create 12 minus 2y equaling y. And as you survey the situation there, it's pretty easy to finish that and be able to find what y equals. So might as well find out that y equals 4. And as you continue to survey the problem, you realize that you're also trying to find x. And if you're trying to find x, you want to take some entries that contain x. And so we have ourselves another very simple subtraction problem. 2x minus, where 2x minus 5y is going to equal -22. All right, and you can solve that for x. Of course, you already know what y equals. And so just take a few moments and process that. And you should be coming up with the fact that 2x minus 20 is going to equal -22. And so we can, again, be able to find x to be -1. Scalar multiplication, distributing a very simple value in front of a matrix, and then addition, subtraction of corresponding entries. Now, it's probably the case that this last operation that we're going to talk about of anything today may require a little additional processing on your part. Matrix multiplication. Why is matrix multiplication perhaps a little bit trickier? Well, I would say it's probably not just common sense. You see, we're not just going to multiply corresponding numbers. Instead, what we're going to do is we're going to multiply a row to a column. So you got to kind of envision an entire row of a matrix, an entire column of a matrix. We're going to end up multiplying a row to a column. And then you're going to find out that there's another piece to this you have to add. And so there's basically two steps, but that's because matrix multiplication, you might say it's two-dimensional. You're actually multiplying two-dimensional objects. Now, I'll show you how to do that, but you just want to see that method. The other thing that I just kind of want to show you before we actually do a problem is that if you have two matrices that are being multiplied together, perhaps matrix 1 has a row and a column, and matrix 2 has a row and a column, what we discover is that the numbers that are in these positions, kind of these inside numbers, they have to be equal in order for you to actually do the multiplication. And it turns out that these outside numbers, they end up making the size of your answer. They will end up determining how big your final matrix will be. Again, I'll show you how to do that with an actual problem, but I do like to kind of give you those specs before we do a matrix multiplication. All right, you ready? Matrix multiplication. Again, it may not be quite what you think, but it would depend on what you think. So let's take this matrix that contains 3, 2, -1, and 4. What we're going to do is we're going to multiply it by this matrix that contains -2, 5, and 0, and 1, -1, and 3. So you can already see that these two matrices, they're not of the same size. But does it turn out that they are of the right size? What do we mean? Well, this matrix is a 2 by 2. It has 2 rows and 2 columns. And this matrix over here is a 2 by 3. It has 2 rows and 3 columns. Now remember, these inner numbers have to be the same in order for you to do the problem. So that's good. They are the same. And these outer numbers, well, they're going to end up being the size of my matrix. They're going to end up being the final size. That is a 2 by 3. So that means we're going to end up with, well, with how many numbers? We're going to end up with 6 numbers. All right. What do we mean multiply a row to a column? Here's a row. Here's a column. What I'm going to do is I'm going to multiply those numbers together. Now, the first numbers that I multiply together would be 3 and -2. And that, of course, is going to end up giving me -6. The next numbers I multiply together are 2 and 1. And, well, that's going to end up giving me 2. So we multiply those matching numbers. But then you add. And after you add those numbers, that final answer ends up going in the first row, first column. Now, the reason it went in the first row, first column was because those were the numbers that I multiplied together. I need to kind of erase a little bit of this so we don't get too messy. Let me rewrite. What did I have here? -2 and a 1. All right. But the fun's not over. It's just beginning, because next I'm going to multiply this row by this column. Okay, you can see that I'm actually now moving over and matching up another set of numbers, where 3 is going to multiply to 5. Now, when I multiply 3 to 5, that gives me 15. And -2 is going to match with -1. And -2 and -1, when they multiply, I get 2. You're going to add those together, and after you're done adding them together, oh, shucks, I didn't realize this was not a -2. It's just a +2. So that means when I multiply these together, I'm going to get a -2. Sorry about that. So I'm going to get 15 and -2. And when I add those together, I end up with 13. Notice that I wrote that number in the first row's second column. Okay, of course, those are the numbers that I was multiplying together. Once again, let me erase some of this. I don't want this to get too messy. Make sure I get the correct numbers, just a positive 2. And finally, I'll move over here to this last combination of numbers. And what numbers am I going to multiply? Well, 3 with 0. Zeros are always nice because 3 with 0 obviously gives me 0. And then I'm going to multiply 2 with 3. And when you multiply those, you end up with 6. Add them together, and I end up with a final entry of 6. Now, have you noticed that so far I only multiplied, or maybe I should say circled, the first row. I circled the first row, but now it's time to move on to the next row. It's time to move on to row 2. And I'm going to take row 2 and I'm going to multiply it by each of these columns. Now, pay attention here because sometimes students kind of incorrectly match the numbers. -1 is my first number. I'm going to match that with -2, which is the first number. So when you multiply -1 with -2, you do get +2. 4 is going to match with 1. Match, multiply, you end up with 4. Add them together, you end up with 6. Feel like you're catching on? Okay, because now we're going to move over to this column. Match -1 with 5. Remember, match means multiply. So we'll get -5. And match, multiply 4 with -1. And when you multiply 4 with -1, we get -4. Add those together, you end up with -9. Move on to your last column. You're going to match -1 with 0, which gives you 0. And you're going to match 4 with 3. Gives you 12. Add them up, and we end up with 12. I know it took a little bit of extra time to show that. I just think it's important that you see it very carefully the first time. Matrix multiplication. You multiply a row to a column, and then you add. Let's try another one. Okay, perhaps maybe you can do a little bit of input on this. Let me give you some numbers, though, so we all have the same numbers. How about 1, 2, 3, 4, 5, 6? And we're going to multiply that by 7, 8, 9, 10, 11, and 12. So what do you think? You guys want to see if you can multiply this one? Okay, remember to multiply, you're going to multiply a row times a column. Now when you multiply a row times a column, you're going to take the first number, 1, you're going to match it with 7. You're going to take the next number, 2, you're going to match it with 9. But what number do we have to match with 11? We don't have a number. That's because you can't multiply these matrices together. You see, students, this matrix is a 3 by 2, but so is this. And when you look at that carefully, you realize, wait a minute, these numbers are not the same. These inner numbers have to be equal. Well, when they're not equal, you can't do the multiplication problem. And so when it comes to the final answer is that there is no answer. But what I want to obviously kind of point out here is that matrix multiplication, it's a little touchy. Some problems can be done, some problems can't be done. Okay, this is a good example of a can't be done. Let's see if you can multiply these as a little bit of practice for our last example. Okay, here's 2 matrices. Just take a careful look at the entries. It's a matrix multiplication problem. You would see a multiplication sign, or else the matrices would just be right beside each other. Now, normally, students, if we were in class, this would kind of be the problem that you would try as like a little exit problem, something that I would probably like to check. Go ahead. You try the problem right now. Pause the video. because when you the next thing I'm going to do is I'm going to show the results. So go ahead and try the problem. Of course, if you need some help, you can play the next scene. See if you can do this last matrix multiplication. Perhaps the first thing that you should do is just double check that this matrix multiplication can be done. This matrix has 2 rows and 3 columns, and this matrix has 3 rows and 2 columns. Well, it looks like it's going to work because these inner numbers are the same. And we also notice that these outer numbers are going to make up the size of our matrix. That's right, our final matrix is only going to be of a size 2 by 2. A 2 by 2 is not a real big matrix, right? So you only need to have enough space for 4 numbers. How'd you do? You're going to multiply the first row times the first column. You should end up with -2, 25, and 0. -2, 25, and 0 add together to be 23. Next, you're going to multiply the first row, but over to the second column. How'd you do? You should get 6, 15, and 0. 6, 15, and 0? Well, those add up very nicely to be 21. Moving on to the second row, but back to the first column. Multiply, match, you should get +6, +5, and +4. +6, +5, and +4 is 15. And our last one here, just need one more color. So we'll go with matching the second row with the second column. You get -18, 3, and 0. -18, 3, and 0 is -15. Matrix essentials. Okay, talked about some basic ideas with equal matrices. We did some scalar multiplication, addition, subtraction, and then, of course, lastly here, matrix multiplication.